let's try to solve another Leetcode problem, 351 Android unlock patterns. So for this problem, I think it's a little bit difficult to understand, and even we understand the problem, it's really difficult to do because definitely we cannot find a pattern. Yeah. So first of all, let's just try to understand the problem. I'm going to use some examples to explain what is the meaning of the problem. So we are giving 3 times 3 grid of dots. Yeah. So this is what we are giving, and it is 3 times 3. And inside the grid, there are going to be 9 numbers. Basically, it is 1, 2, 3, 4, 5, 6, 7, 8, and 9. Yeah. And then we're going to use the lock and unlock pattern. So if we lock the full, we can start from any numbers. So for example, we can start from 1, or we can start from 7, or others. Yeah. So let's just continue. I'm going to use some examples. So let's just check the first pattern, 4, 1, 3, 6. So 4, 1, 3, 6. This is invalid. Why? 4 to 1, it is okay. 1 to 3, because there's a 2. But for our pattern, there's no 2. Definitely, we go through this 2. We needed to have a 2. That is why it is wrong. And let's just check another pattern, 4, 1, 9, 2. 4, 1, 9, 2. 4 to 1, it is okay. But what about 1 to 9? 1 to 9, there's a 5, but we don't have a 5, so that is wrong. And let's just check other patterns. 4, 2, 1, 3, 6. This is 4, 2. Let me use another color maybe. 4, 2, 1. Okay. And 3. This time we can go to 3. Why? Because we've already visited 2. This is okay. So we can go to 3. Yeah, because this is just the definition. It means we've already goes to 2. If we go to 2, so 1 can go to 3. If we didn't visit 2 before, 1 cannot go to 3. So this means we can go to 3 and 6. So this is another pattern. This is valid. Yeah. Now let me just go back. And the last pattern is 6, 5, 4. So 6, 5, 4. It is okay. And 1. Okay. As 5 already be visited, so we can go to 9. So this is okay. Otherwise, we cannot go to 9. Yeah, so definitely if 6 were to go to 4, it must visit 5 before. So this is why we have a 5. 6, 5, 4, 1, 9, and 2. Can this 9 go to 2? Yes, it can. Yeah. Because 9 to 2, it didn't visit 5, and it didn't visit 6, it doesn't matter. 9 can directly go to 2, and this is also valid. And what we're gonna calculate? We just want to return how many different combinations with giving m times n. It can. So what is the meaning of the m n? So here, given 2 integers m and n, we're gonna return the number of unique and valid unlock patterns of the Android grid lock screen that consists of at least m keys and at most n keys. So what does that mean? It means we're gonna get a number. So for example, it's gonna be let me use another color. Maybe we're gonna use a number, maybe x. So this x is gonna be less than or equal to n, and more than and equal to m. And for the first example, it means just we need 1 step. And for the second step example, it means we can need a 1 step or 2 steps. That is okay. It means we can have a pattern of 1, or we can have a pattern of 1, 2. That is also okay. We just need to check the combinations. And for this example, it's going to be 65. And for the first example, we just need to return numbers from 1 to 9. So it's going to be 9. Yeah. And we need to know how to make this case like from 1 to 3. How should we know from 1 to 3 and this number 2 should be visited? This is difficult to do. Yeah. If we were to go from 1 to 3, this means the number 2, we must know this number 2 is visited before or not. So we're going to use the bit mask dp. We're going to use the state to mark this 2 as visited. Then we can go from 1 to 3. Yeah. So this means we can design a graph So inside our graph, we're gonna prepare the numbers like 1 to 9. Yeah. And for this number 1 can go to different numbers. So for example, 1 can go to 3, but we need to know that this number 2 should be visited before 1 go to 3. So we can prepare another number. It's going to be 2. So this is the basic pattern. We have a 1 to 9, and then if we were to visit 3, this means the 2 has to be visited. So for this case 3, it have another value on 2. If we can design such kind of a graph, basically we know how to solve the problem. Yeah. Now let's just start coding to check if that is possible to design such kind of pattern. So the pattern is just like from number 1, we can go to some other numbers, and let me just copy and paste to prepare all the different cases. Yeah. So basically, I need to prepare 9 numbers, like 1, 2, 3, 4, 5, and 6, 7, 8, and 9. Yeah. Now we're gonna design the graph. So what about this number 1? 1 can go to 2 directly, right? But we don't need to record that because it doesn't matter, because 1 can directly go to 2. But what about if 1 go to 3? We have to record that 2. This means the 2 has to be visited before 1 go to 3. Yeah. So 1 go to 3, we have to remember a 2, and 1 can go to 7, we have to remember a 4, and 1 can go to 9, we have to remember a 5. So this is the basic design pattern for our problem. Yeah. As 1 is symmetric to 7, 9, and 3, so let me copy it here. 7, 9, and 3. And similarly, we can do for this 3. So 3 can go to 1, so this 2 has to be visited, and 3 can go to 7, and 5 has to be visited, and 3 can go to 9, this 3 can go to 9, and 6 has to be visited. Yeah. Similarly, let me do it from here. 7 can go to 3, so 5 has to be visited. 7 can go to 1, 7 can go to 1, 4 has to be visited, and 7 can go to 9, 8 has to be visited. Yeah. And similarly for 9 can go to 3, 6 has to be visited, 9 can go to 7, 8 has to be visited, and 9 can go to 1, 5 has to be visited. Yeah. Now we're going to prepare the number 2. So 2 can only go to 8, and we need to remember a number which is going to be 5. Yeah. And similarly, let me just copy and paste for others. What about 4, 6, and 9? Yeah. So for 4, this number 4 can go to 6, and 5 has to be visited, and 6 can go to 4, 5 has to be visited, and 8 can go to 2, 5 has to be visited. We have to remember such numbers like here, visited. So what about number 5? So for this number 5, it can go to anywhere, it doesn't matter. Yeah, because there's no constraints, there's no restrictions. So for this 5, definitely it can go to all other numbers directly. But for this number 1, if it was to go to 3, this 2 has to be visited. So for this number 2, this is exactly what we are going to remember. Yeah. So this is the most difficult part. We need to design such kind of data structure. It is a graph, and inside a graph we have to remember something. It is not only like 1, 3, 7, 9. We have to remember this like 2, 4, and 5, which means it has to be visited before we visit this number 3. 1 to 3, we have to visit 2. Yeah. Now we're gonna use the bit mask to start the dynamic programming part. Yeah. So we're gonna prepare a function. And what about how to define this function? We need to use a bit mask. So we're gonna prepare a state, and we're gonna prepare the current number. So the current number, it means I'm gonna start from number 1 or number 2, and we're gonna prepare a count. as we are going to count how many numbers we visited, so for example 5 or 4 according to this m and n, and we also need to prepare a target. The target is something between m to n. Yeah. So the condition is that if the count equal to target, it means we've already filed, so we're gonna return a 1. Yeah, so this target for the first example, the target is 1. For the second example, the target can be 1 and 2. Yeah, now we're gonna start the main part of the bit mask. Yeah, so we're gonna set a result to be 0, and then we're gonna check how many different cases. So for all the numbers, it's gonna be in range from 1 to 10. Basically, it means the numbers from 1 to 9. So if this number is not visited, so how can we check if this number is not visited? We're gonna use a state and. Yeah. So 1 left shift I positions, if this is equal to 0. Yeah, let me think about it. Yeah, so if this equal to 0, so this means this number I is not visited, and then we want to visit it. Yeah, so and not, we're gonna check if it is inside the graph or not. Yeah, and not G. Yeah, let me think about it. And not the current. So this graph, so this G is for the graph. The current, it may have be a number. This current may be a number 5. Yeah. So if this current is 5, it means it can go to anywhere directly. We don't need to remember anything. Yeah. So if not the current, it means it is empty. So definitely, so this means if this number is 5, so definitely it is okay for us. So yeah, we can just update the result. It's going to be F. So here we're going to copy it. We're going to put it inside the mask, inside the state. It's going to be add with this one. And the current going to be I, and the count going to plus 1, as we added with one more number, and the target going to be the same. Yeah. Finally, we're going to return the result, but this is only condition for number 5. So what about number 1? So what about so what about the current is 1, and the I is 3? I want to check if from 1, can I directly go to 3? This means 2 has to be visited. How can I check that? Yeah, so this is another case. If not, or G current. So current is 1. Yeah, if not the current, it means empty. Otherwise, inside the current, it has something. And definitely, I'm gonna check this I. Yeah, so I'm gonna check this number 2. If this number 2 is visited before or not, so I'm gonna use the mask. I'm gonna use the bit mask to check. Yeah, left shift 1. Here I'm gonna use add the state. Yeah, so this is the second case. So if this number, for this example, this number 2 is visited before, so I'm going to add the state. Yeah, so this means if it add state equal to 1, so basically this means it has already been visited before. Yeah, if this 2 is visited before, so this means I can add 3 into the state, into the set. So this is why I can add this 3 into the set, because G current I is this number 2, and this this I is 3 and the current is 1. Yeah, I think it's a little bit confusing to understand, but definitely we need to prepare so many variables to solve the problem. Yeah, if it is not inside, definitely we can put it inside. The hard part is how can we understand this bit mask. Yeah, if this number is not visited before, we have to visit it. And for this 1, 2, 3, we have to visit 2 before. So this is why we're going to check it from here. But if everything is okay, it is a 5. We can directly check that. It's not the current. So definitely we can put it inside. Yeah. So for example, if this 5, so this I can be any number. So for example, this number I can be from 1 to 9. Yeah. And the current is 5, if not the current. If inside this G5, it is empty. So basically it means from 5, and I can go to anywhere. If 2 is not visited before, so 5 can go to 2. If 9 is not visited before, 5 can directly go to 9. Yeah. I think basically we've already finished the coding. So finally we just need to return the final answer. So how can we return it? So we can start from our numbers from 1 to 9, and then we're gonna check all the target. So this target is gonna be from for x, maybe x. Yeah. So in range from m to n plus 1, and the result is gonna plus equal to the function, and we're gonna set the result to be 0. So inside the function, we're gonna use the state. The state is 1 left shift with I. Yeah, so this means basically this is the beginning of the state. If we are starting from 1, so inside of the set, we need to put this number 1 inside of the set. So basically the state is also a set. Yeah. So we put it inside, and we're gonna use the current number, which is gonna be I, and we're gonna use the count. We're gonna count it as 1, because if we use one number, it's gonna be 1, and then we're gonna plus it. Yeah. And the target is gonna be x. Finally, we're gonna return the final result. Yeah, it is a lot of coding. So basically the main part is preparing this graph, and also the bit mask. Now let me just run it to check if it works. No. Yeah, so let me make a comment about here. I think there must be something wrong with here. Yeah, if I uncomment it, at least I can let the code running. But here is something wrong. Let me just check why it didn't work. So if not, yeah, I have to check this is not visited. So for yeah, maybe I use processes. No. So there's something wrong. Let me check. Yeah, but I cannot use the current with I. Yeah, I have to. Here is something wrong, I think. Because for this I, I'm not sure if it is inside the dictionary or not. So here it's not G current. So if I not in G current, this means if I not in, otherwise so I gonna be inside the current, and then I can use it. Yeah. So if this I not inside G current, so for this example, G current gonna be empty. So from 1 to 9, it is not. Definitely, it is not. Yeah. So here is something wrong. Now let me just run it. So this is invalid. If I not in, yeah, this is invalid. Let me just fix the grammar issues. Now, as you can see, it works. Yeah, I have to check if this number I is not inside the G current. So for example, G5, it is empty. So from 1 to 9, it is not inside. Yeah, because in other cases, so for example, this is 7. There's still gonna be other cases. So for example, if it is 7, I'm not only checking like numbers 3, 1, 9, but I also check other numbers. So what about other numbers like 2? I still need to check that. So this is why I have to use I not. Because it is not only about number 5, it can have some other numbers. It has to, for this number 7, it has to check another 9 numbers instead of 3. This is why I made a mistake about here. Yeah. Now let me just run it to check if it works. Yeah, as you can see, it works and it's pretty fast. Now let's analyze the time complexity. So let's just analyze from the for loop. So this is a 10, right? And here is mn. Mn gonna be 1 to 9. So this is another 10, right? So 10 times 10 and times the bit mask, the dynamic programming part. So this state is so basically this state is 2 to the power of 10. Yeah, and for the current, it can have just yeah, 10 numbers. So we're gonna times 10, and for this code, it can from 1 to 10. We're gonna time another 10, and what about the target m to n? It is another 10. Yeah, it's 1, 2, 3, 4, 5, 10 to the power of 5 times 2 to the power of 10. It's really big, but it is not like that because yeah, because for this target, actually, if we are checking the target, everything is remembered. It is not 10 to the power of 5, it may be 10 to the power of 4, I think. Yeah, I think it may be 10 to the power, it is not 10 to the power of 4 times 2 to the power of 10. Basically, it is 10 to the power of 3. That is why it works. And because for this target, for example, if we are calculating this target 9, and while we are calculating with this 8, basically we've already calculated from 1 to 8, and for 9 it is also okay. So we can remove this part for the target because it is dependent on this this for loop, and because we are using the cast, everything is remembered. So we're going to only consider the state and also the current and count. Yeah, so the time complexity is going to be 10 to the power of 4 times 2 to the power of 10. It's going to be this one. Yeah. I think that's all about it. Thanks for watching. See you next time.